if G is from GLV is an nilpotent Lie subalgebra, is it okay? Is an nilpotent Lie subalgebra consisting of nilpotent elements, Lie subalgebra, and for any x from G, x is nilpotent, then it implies that there exists common eigenvector for any x from G, x dot v is equal to 0. So there exists common eigenvector for entire Lie algebra. Okay, is it clear? So we consider nilpotent Lie subalgebra of GLV such that any element of this algebra is nilpotent linear operator itself. Then there exists common eigenvector. It is not true for any subspace. If you consider any subspace consisting of nilpotent operators, it is not always possible to find a common eigenvector, but if this is nilpotent Lie subalgebra, then it is possible. In other words, it means that in this case, G is subset of n plus in some basis. N plus is strictly upper triangular matrices. Okay. And second point is what I formulated. G is nilpotent if for any x in G, and x is nilpotent. Okay, and let's prove it. So yeah, mostly it's this. Is the statement clear? It's like what we can, as I said. So we have an like most common example of nilpotent Lie algebra is Lie algebra of strictly upper triangular matrices. And it is the best what we can say for any field of any characteristics that, okay, for some particular Lie algebra, they are subalgebras of n plus. Unfortunately, it is not true for any nilpotent Lie algebra for arbitrary, in arbitrary case. Okay, so proof. The proof is let's prove by induction by dimension of G. Okay, that G is equal to 1, it is obvious, right? It's a nilpotent operator, it has eigenvector. It has kernel, I mean, so for in any field. That's clear. So now let's do the step. Let H from G be a maximal Lie subalgebra. Okay, just maximal Lie subalgebra. Maximal proper. Let's consider maximal proper Lie subalgebra of Lie algebra. Like it exists. It is not non-trivial because any element spans some Lie subalgebra of dimension 1. So it is at least of dimension 1 for sure. So it is something. Then consider adjoint representation. Yeah. Proper, it means that's собственное. Adjoint representation of GLG. Then, if so, we consider adjoint representation, and H inside G is okay. First step, and restrict it to H. It will be from H to GLG. So consider restriction. Then let's say that for this restriction H inside G, then H inside G is sub-representation, right? It's invariant subspace, and so what? Let's recall what is adjoint. Is it clear? Or let's recall that it maps any element to. And we discussed last time that from Jacobi identity it follows that it is really a representation of Lie algebra. So then H from G is sub-representation. Right? Because it's stable and the commutator. Not with any element because it's not ideal. But if we restrict, then it is stable. Then we can consider then G over H is also representation. Representation of H. Okay. Okay. So now, we get some. So H. We get some homomorphism C from H to GL G over H. Okay. Now consider image of H. Let's consider image, okay, C of H. What we can say about C of H. So I want to apply induction hypothesis for C of H. Okay, C of H is some subalgebra in GL G over H. Okay, dimension of C of H is less than dimension G. Okay. Now, moreover, what else? So we have subalgebra. Is this subalgebra nilpotent? Yeah. So we consider maximal proper Lie subalgebra of G. G is nilpotent subalgebra. Then H is nilpotent as well. Subalgebra and homomorphic image of nilpotent is nilpotent. So Psi of H is algebra. Psi of H is nilpotent. And is it true that it consists of nilpotent elements? Okay, because originally we have nilpotent elements. All elements of H are also nilpotent. Image of nilpotent elements are nilpotent, and in factor, if it was a nilpotent element in the factor, it's still nilpotent. So it consists of nilpotent elements. And all elements. This is because we have that's true. That yeah, you're right. Sorry, right. Here we use the following lemma, right? Thank you. So if X is nilpotent, then add X is also nilpotent. Okay. Here, yeah, thank you. So I have to say this. So this is just some statement. Okay, if X is nilpotent, then add X is also nilpotent for any nilpotent element. So X from endomorphisms of V is nilpotent. Then add X, which belongs to endomorphisms of V, is also nilpotent. Do you know why? What is add X? It maps Y to xy minus yx, right, in this case. So this you can, so you have two operators, multiplication from the left to y and multiplication from the right, and they commute. But this is obviously nilpotent multiplication, so if you multipy enough times, then you get 0. This is nilpotent, and this is nilpotent. And this is sum of two nilpotent operators. This is nilpotent, this is nilpotent, this is sum of two nilpotent operators. Of two nilpotent commuting operators, and sum of two nilpotent commuting is also nilpotent. Because okay, you can do this okay, you like how it called binom Newtona. Okay. Newton's identity or something like this. Newton's binomial. Okay, yeah, thank you. So here I use this implicitly. You understand how I use this? Because okay, it's a joint representation. X is nilpotent, and X is also nilpotent, and then I proceed to quotient, and it's still nilpotent. Okay, yeah. So therefore, I can apply induction hypothesis to this C of H. So there exist V from what is notation here? Oh, that's X. Okay, there exists X in G over H, such that okay, y dot x is equal to 0 for any y from H. Right? Or okay, maybe let's write C of y. We just find common eigenvector for all elements now. And what does it mean? It really means that let's go back from this procedure. What we get that what we can say about commutator of y and x? Belongs to H. But for any y from H, commutator of y and x belongs to H. Okay? Very good. So it means that, but what does it mean? Then consider the following subspace H plus C dot X. It is Lie subalgebra, right? Because commutator of H of two elements from here is here. From here it is 0, and from here and here it's again in H. This is Lie subalgebra. It follows that is a Lie subalgebra. Moreover, H is subalgebra inside this guy, but H is maximal. What does it mean? That it is G. Yeah. Therefore, H plus Cx is equal to G. Because H is maximal. Okay. And we are almost done. If you are still not understand what we are doing, we are about to prove Lie theorem, and we will proof will be almost the same. So yeah. Yeah, we applied for algebra C of H inside G over H. Yeah. You can ask in Russian, it's easier. So we applied here. So dimension of C of H is less than dimension of G, and that's it. So induction on dimension of G, just. Yeah. Here it's not necessary to. It's like if you prefer full induction, so it means that not necessarily it's less. It could be less on so more than one, but anyway, so it's full induction. You can use not only for previous, but for any statement for any n. Any other questions? So now you can. What we can do now? We can. H is some subalgebra, so as you want, but again, so H now is dimension 1 less than. So as you prefer, now we can use our induction hypothesis for, in this case, so for H, we can find common eigenvector, right? There exist, again, by induction, there exists V from V such that x over V is equal to 0 for any x from H. Okay? Oh, not x. Okay, x is bad. Y. Okay, we do not apply y. Y. Okay? And we almost, so now if we can say that it's also eigenvector for x, we are done, right? Because our algebra is H plus something. So it's enough to show that x they exist. Okay. Denote by with 0 the subspace of vectors V such that x dot V is equal to 0 for any x, y, for any y from H. It is non-trivial because we have at least one. It could be some dimension, we don't know. So it's enough to show that there exists V from let's say W from V0 such that x on W is equal to 0. Right? It's enough. But let's compute what we get if we apply x. Let W from V0, and let's try to check what we get if we apply x to W. So we claim that x maps V0 to V0, and then we are done. If x maps V0 to V0, then it has some eigenvector, something in kernel because it's an important operator. Okay. So it's enough to check. It's enough to check. Okay, it's enough. It's enough to check that x maps V0 to V0. Okay. Let's consider some vector, and we want to show that y x v. We want to show that it is 0, right? So for let v 0 and y from H. We want to show that for any y from H, y x v is equal to 0, right? And this is common procedure in lead theory. If you have something, you should compute. So let's compute x y v plus y x v. Okay, this is 0 because y acts on v by 0 because v from v0. And what we can say about commutator of y and x? It belongs to H. Then it is also 0. So we are done. So in fact, x preserve v0. Therefore, it has something in kernel. So we are done. Okay. So yeah. You mean that where we use, let's see, where we use that G is nilpotent Lisa algebra of GLV. Here, if we apply it for any, add x is not necessarily nilpotent, so we cannot proceed from adjoint to this one, because for arbitrary x it's not necessarily nilpotent. Or okay, maybe you're right that we only So here we use that the subspace which so we use that it is Lisa algebra for sure. We use that it consists of nilpotent elements also. So where we use that it is nilpotent. So why we cannot say that it is just Lisa algebra consisting of, but consisting of. Where we use the fact that our subalgebra G is nilpotent subalgebra. Yeah, right. But yeah, I see. Right. So here we use this lemma, but it's only so suppose that we have Lisa algebra consisting of nilpotent elements, just of nilpotent elements. Then we can do this, and this. That's true. Right. But okay, let's think if we have Lisa algebra consisting of nilpotent. So yeah, we do not really use. But it's always like for any, it's always exists some proper maximal Lisa algebra. Yeah, I think that if you have subalgebra, Lisa algebra of GLV consisting of nilpotent elements, then it should be nilpotent. It's yeah, let's see. In principle we didn't use it, but like we will prove that it so in fact it's the same condition. So you're right that we didn't use that it is nilpotent. But like let's prove first step without nilpotent assumption. Then we can prove the second step. Then it follows that in first it is nilpotent. Yeah, we didn't use it. It is nilpotent. You're right. It follows, right? Because we just. Yeah, you're right that maybe it's better to formulate it without nilpotent. Then it will follow it. A posteriori we will have it. Okay, now let's. So probably see here. I do not need this. It's. Just Lisa algebra consists of nilpotent elements. Thank you. Then let's prove the second proof of 2. Okay, if G is if G is nilpotent, then any element is add x. Add x is also nilpotent. We know it. It follows from definition. Let's do it. Reverse order. So consider a joint representation. We know that kernel of a joint representation is center of Z of G. Then what we know? Consider that we know that image of G is isomorphic to G over center. So now what we know about image, right? So it is a Lisa algebra which consists of nilpotent elements. image of G is Lie subalgebra. Lie subalgebra. Algebra consisting of nilpotent elements. Good. Then we can apply previous step. And from previous step it follows that this Lie algebra is nilpotent, right? Because it's subalgebra of n plus, any subalgebra of nilpotent n plus is nilpotent Lie algebra, then subalgebra of nilpotent is also nilpotent. So therefore G over G is nilpotent. Nilpotent by 1. So therefore, as we know, if G over center is nilpotent, then G is nilpotent as well. So it's a property. Okay. Yeah, you're right that we do not need nilpotent assumption here. Okay. Just any Lie subalgebra consists of nilpotent elements. Moreover, we give a proof that it is nilpotent. Okay, any questions? Now we are going to prove Lie theorem, and we more or less we will do the same. We will play the same game. So, moreover, for Lie theorem, it's like Lie theorem in some sense better because for nilpotent Lie algebras. Okay, but for nilpotent Lie algebras we did it for any field of any characteristic. It's not necessarily algebraically closed, but Lie theorem has some restrictions. Okay, what can I erase? I think I can erase this. So this is some characterization of nilpotent Lie algebras. So Lie theorem. So I want to formulate it again with two. Yeah, first of all, we will give a proof only for algebraically closed field, however, of characteristic 0. However, it is true for any field of characteristic 0. But for us it's enough to give a proof. Maybe I will give it as some problem in your exercise sheet to prove it for any characteristic. And let G on GLV be a solvable Lie subalgebra. Then there exists V from V such that X of V is equal to lambda of X not V for any and lambda for any X from G. There exists common eigenvector. It follows that this Lie algebra, in some, if you choose basis, it is subalgebra of upper triangular matrices. Okay. Or we can say that we classified all irreducible representations of a solvable Lie algebra. They are all one-dimensional. Okay. Okay. So, yeah. Yeah. Okay. So, proof. Let's analyze what we did last time. The proof consists of we have 4 steps. First step, we choose something of codimension 1, and it was hard for Angel theorem. For Lie theorem, it's obvious. Let's consider E of G is ideal of here it will be ideal of codimension 1. So first part of proof, we trying to choose something of codimension 1, but it was not ideal. It was subalgebra, but here I want ideal. Then I say that there exists common eigenvector for I. And in the previous step, it was obvious it was induction hypothesis, but here as well, here it will be induction hypothesis, right? Choose something of convention 1, then consider common eigenvector or common also. No, it was also common eigenvector. Here it's clear why I want to something of why I want algebraically field to be algebraically closed, right? Because otherwise I can't find common eigenvector. But this is still not clear why. Third, I want to say that, and let V, the space, let V be, not V, let W be the common, be a common eigenspace. Then, third step was that we gave a proof that entire algebra maps W to W, right? W was V0. So W is invariant under G. So G maps W to W. And the last step that is there exists common eigenvector for G. It's obvious now. Again I used algebraic closure. So, and when we are trying to prove Engel theorem, the hardest step was step 1. Yeah, and then everything else was smooth. Now the hardest step will be step 3. But so in fact we will do the same. Is it clear that it is our scheme of how we prove Engel theorem? And now is our scheme how we want to prove Lie theorem. First of all, the step 1. Okay. If we have step 1, step 2 is obvious, and if we have step 3, step 4 is obvious, right? So now what about step 1? Why we always can find ideal of codimension 1? G is solvable. Then what we can say about G over GG? Abelian. Okay, no. Okay, it's always abelian. Yeah, it's abelian. No, we here. Okay. Okay, you're right. We didn't use it. G or this factor is abelian. Then we have projection. All right. We have projection P, and we can consider something. Here you have ideal. Any element is ideal. Okay, ideal. For any x from G, this is ideal, right? Because it's abelian. Then one can consider preimage of this Cx. Okay. No, sorry. So let be the ideal of codimension 1. let's consider ideal of codimension y inside this abelian algebra. So any subspace is ideal. So let's consider just subspace of codimension 1, and let's consider preimage of the preimage of this. Right? Then it is ideal. Preimage of ideal is ideal, and it's again ideal of codimension 1 in G. Yeah, y codimension 1. So let's, yeah, I think it's obvious of codimension 1. Because what? Yeah, probably here I want to use something. Why it's indeed of codimension 1. Ideal. Let's consider preimage of ideal of codimension 1 is ideal of codimension 1. So it is not always true, right? So if I consider some Lie algebra and its abelianization and consider preimage of something, no, that's interesting, because otherwise why we cannot do the same for in the previous case, right? Like why we cannot? But like, I mean, probably we can, but we need some more. So we use some special representation here. Yeah, probably we can. One. Mm-hmm. So this is, so we have solvable Lie algebra. Center is non-trivial. So you suggest, so that it's not true that we can always. So if you have, so you cannot split. You cannot split arbitrary algebra into center or something else. Yeah, that's a good question. So we want to consider ideal of codimension 2. So how we can find ideal of codimension 1? How we can find ideal of codimension 1? But let's check. It is not. It is not true. You say that. Why is it not? Yeah. Yeah. No. Sit. Yeah. You can say. Yeah, I think this is obvious, right? It should be obvious. Yeah, this map is surjection. So suppose that, okay, so this idea of codimension 1, suppose that it is, suppose that codimension of p minus 1 of I is greater than 1, right? Let's consider p of p minus 1 of I, right? What we get? We will get I. We will get I. And what does it mean that this codimension is greater than 1? It means that dimension of G or pi minus 1 of I is greater than 1, right? Then what we can say about, so it's some homomorphism theorem, I don't know, third homomorphism theorem. So then dimension of so this dimension is greater than 1. So if we map, means it's like it. So how to say strictly? Rejection, not subjective. Okay, so this, if you consider pi minus 1 over I over GG, right? This is ideal inside G over, right? Well, sorry, pi minus I. It's like, okay, this is just some obvious. So if you have vector space, you have to, okay, let's say if you have vector space V and U is vector subspace, right? And you consider map from V to V over U, right? Then and consider some subspace here. Then dimension. Okay, dimension of so what we want to say that if, okay, suppose that dimension of V W is n minus 1 and dimension that's the dimension of okay, W, here you have W, here you have some X, let's say. Yeah, that's true. So yeah, how we can? So we have to use that it is solvable, right? To use it is solvable. Subspace. So let's check. No, we can't apply the same because we use some different argument. So it's not enough to have idea of codimension 1. Yeah, right. So probably, so what I want, so G is solvable, right? And I claim that in solvable Lie algebra I can find idea of codimension 1. Why? In solvable Lie algebra is idea of codimension 1. How to find idea of codimension 1 in solvable Lie algebra? Yeah, probably. So indeed we have center, non-trivial center, but so we have trivial center, but okay, for nilpotent Lie algebra we also have non-trivial center. Okay, anyway, all right. Let's indeed have I, and let's have p minus y of I. I claim that if G is solvable, then it is ideal. This is a claim, right? So I claim then the yeah. So we claim that P minus 1 of I is ideal, right? What does it mean? So I have to check that X P minus 1 of Y belongs to P minus 1 of Y for any X from G. So I have any substance. Okay, so if I apply pi, it's pi x. Yeah, that's true. George Jason. Okay, we know, so probably I want to use something like this. We know that GG is solvable and that GG is solvable. Then, so I know this. It means that, yeah, I know, so that GG is solvable, it follows that GG over commutator is also abelian. This is abelian. And it should follow from this, it should follow that this is an ideal, I think. How it follows that P minus 1 of Y this is homomorphism. Yeah, how can we choose indeed ideal of codimension 1 in solvable algebra? Like the claim that any solvable algebra has ideal of codimension 1. Ah. You mean, yeah, we can take any subspace of codimension 1 which contains commutant. We did it. So so what we did, we consider any subspace of codimension 1 which contains commutant. Like we already did, and we want to prove that any subspace of solvable algebra which contains commutant is necessary ideal. Indeed. Why it is necessary ideal? It contains commutant and yeah, that's obvious indeed. So if we have I, okay, let's G, we consider I which contains commutant, and we claim that I is ideal. We want to check that X I belongs to I, right? Why it belongs to I? Right. That's true. That's obvious. Thank you. Yeah, it's XY belongs to GG. It's always true. Any subspace containing commutant is always ideal. So we can G is not equal to GG, if G is equal to GG, then our Lie algebra is abelian, and for abelian Lie algebra we know that. No, I mean if it could be if it's abelian it's also okay. If it's abelian it's also okay. Yeah, the only problem if G is equal to GG, then we cannot do anything. But G is not equal to GG. Yeah. Okay, thank you. So, yeah. It follows that. Yeah, for simple algebra, we have for semi-simple algebra, G is equal to GG. So yeah. Exactly. Okay. Yeah. Thank you. So now we see that okay, we always have idea of codimension 1. And for Engel theorem we cannot use it because okay, if we don't have nilpotent assumption, then we cannot use it. Okay. So second step is obvious. Now we can now we clarify the statements of our propositions. Now we have for any but it's obvious. It's always hard to explain obvious things, right? For any x is y, where there exists v from v, that x times v is equal to lambda of x v. That's true. That's okay. And now let's recall how. Okay, therefore let's w be agent like be v from v such that x over v lambda x times v for any x from I. And now let's recall what we did for nilpotent. The third step was simple. Now it's enough to prove if this space is invariant under action. Again we can write that G is I plus Cx Kx y Again, we want to prove that it is invariant under the action of x. Okay, let's check x. Let's v from w. Okay, w from w. We consider x dot w, and we want to prove that y x w. We want to prove that y x w is lambda lambda of y. Okay, we want to prove that it's lambda of y times xw. But let's check it. Let's compute again. So it is xyw plus xyxw. And this is indeed lambda of y xw. And this guy belongs to, so I is ideal, right? Then yx belongs to I. Therefore, it is equal to lambda of yx w. Okay? And what we want to prove? We want to prove that this guy is 0. So it's we want to prove that lambda of yx is equal to 0 for any y from I and x from x is for any y from y. X is concrete element. Let's prove it. What I want to do is like, so this is some linear algebra. So in linear algebra, let's recall how we proved that the space of the set of commuting operators have common eigenvector. We consider something like vector x times vector x squared times vector and so on. Let's play the same game. Let's consider the following subspace. let's let fix W from W and consider the space. Let's consider Wi space, which spans by W x times I minus 1 W. The space spanned by these guys. What I want to say is that Wi is invariant. Oh, sorry. So it should be x. Why? Oh, x is bad. Sorry. Let's. No, it's this x what we want. We claim that Wi is invariant. With respect to y. Okay. Let's see. So I want. It's necessary to prove that y x to the n w is some linear combination of these degrees. So we already see. So we did it for v. For v0 it's obvious because it's agent space. For v1 we did it here, right? So this linear combination of this and this. So this is something times w plus something times xw. Let's do it for w2. I want to show that y x squared w has the form like something times x squared w, something times xw, something times w. Okay, just commute again. So it is x yx w plus yx xw. Is equal to x squared yw plus x yx w plus yx xw. If you want, so probably here I can apply okay, let's do it. It's some commutator of so it is x yx w plus commutator of yx x w. And let's see what we have. This is equal to lambda of y x squared w. This is equal to lambda of yx xw. This is equal to lambda of yx again xw. And this is equal to lambda of this big guy times w, right? Okay. So let me. Then you can proceed by induction and prove that it is true for any n. Okay. So proof for any n by induction. But it's more or less clear that, in fact, it's not necessary probably to write it here like this. I can apply induction hypothesis here and just say that. I mean, it's not here. Here I can apply induction hypothesis because yx belongs to I, and then if the space w1 is invariant. So this is just some linear combination of xw and something times w. But like it's not necessary really to write it like this. Okay. Great. Now it means that it follows that y in some basis has the following form. How it looks like? this is some flag. Yeah, we have operator which preserve flag. Then y, it follows that y in some basis, okay, in this basis has the form lambda of y something 0, right? Okay, in some basis of w. Because they are always linear independent. If xw is equal to x to the next one, then they are always the same. Then let's compute trace of y. It is equal to what? N times, n is dimension of this space, I don't know, okay. N is dimension of w. N times lambda of y. But at the same time, it is equal to what? This is for any y from I, right? And let's recall what we want to prove. We want to prove that this is 0. Let's apply this to y, to commutator of y and x. N lambda of yx, and is equal to what? Because commutator of any trace of commutator is always 0. Let's trace of xy is equal to n lambda of xy. This is equal to 0. It implies that lambda of xy is equal to 0. Here you see where we use the characteristic assumption. Here I use that characteristic as 0. Otherwise it is not true. Okay, we are done. But yeah, no, we only use that it is invariant in the direction of y, so it's enough. No, here we use that commutator belongs to I as well, because I is ideal. Here we use the fact that I is ideal. Yeah. Mm-hmm. No, we consider, so let's see what we proved. We consider any y from I, and we prove that it is invariant, this flag of subspaces is invariant under y. And for any y in some basis, it looks like this. Is it true? So now we apply this statement for y is equal to commutator of x and y. It has some matrix like this on this space. Do you know how it looks like commutator of these matrices? It's always strictly upper triangular. It has matrix. It has matrix, this matrix. We consider already restriction. Like we work with restriction from the beginning. We do not consider xy as operator somewhere. We consider it's already there. So we have matrix of xy on the space spanned by these degrees. It looks like this. So yeah, so once again, so maybe you're right. So you said that, okay, I want, so what I said, I want to say that this is equal to this, right? But here I use the fact that trace of commutator is 0. Yes, maybe you are right. I should say something here because if you have, but yeah, I use this fact that this is, if you have two operators, then they act on the subspace as commutator of these two operators. So because just by definition, it's like composition of two minus composition of two other. That's from here I use it, but it's like it's obvious. If you restrict commutator to subspace, it's commutator. That's true. Yeah, here I use it. You're right. Okay? Yeah, so here, so you can relax this assumption. But it's some work. We only give a proof for algebraic closed field. Okay. Where we say that there exists a common eigenvector everywhere. Where we say that there exists common eigenvector for y. Where we say that there is common eigenvector for entire G. Everywhere. The difference between Angel theorem and Least theorem, because if operator is nilpotent, it always has kernel. If operator is something, it's not necessary. It is not necessary that the operator has eigenvector. It's only for algebraically closed field. Okay. So, any other questions? Yes. Okay. So, but here we use. Yeah. We use the fact that we have some space and some operator on it, and we say that it has eigenvector for x. Yeah, here for y it's already here we use it for x. Yeah. Any other questions? Yeah, here I use the restriction of commutator if commutator is commutator of restrictions. Okay, so this is Least theorem. Okay. But as you see, the proof is entirely parallel to the previous one. Now we can give some definitions. Okay, so what I want to say. All right, so I send this. Okay, now let's. So we have characterization of solvable algebras, and once again, let's recall that we have radical of G is maximal solvable ideal. But let's characterize this solvable ideal in some terms. Why it is bad part? So if again we study structure theory, we have Lie algebra G, we have maximal solvable ideal, we have semi-simple. The quotient is semi-simple. Good. Why radical is bad part of algebra, and why we in our course we want to study only this part. Let's give some characterization of this radical in terms of representations. Proposition. Let V be an irreducible representation. Reducible representation of G. Then there exists lambda. Lambda from linear. From radical G star, such that for any V from V, x times V is equal to lambda of x. Okay, it's some analog. It means that radical in any reducible representation of Lie algebra, radical acts by scalars. It's like it's not really important part of your algebra in terms of action on representations. Moreover, for any x from G, from commutant of G and radical G, we have x dot v is equal to 0. Oh, for any v from v, and here, okay, here I wrote. So it means, yeah, further we cannot, like, again, if unfortunately you don't know any structure theory of associative algebras, but like if you know the structure, then you know that you can say some it is possible to distinguish two elements of Euler algebra by their action on finite dimensional representations. Here it means that you could consider all irreducible finite dimensional representations, and you can distinguish between elements from this guy. And this is really bad thing. So you cannot distinguish elements by their action on irreducible representations. So мы не можем различить элементы из коммутанта G, из коммутатора G и радикала G с помощью их действия на неприводимых представлениях, потому что они действуют нулем, на любом неприводимом представлении. Это не очень хорошо. But it's some characterization. Let's prove. The proof is like exercise on Lee's theorem. Let's prove. So we have Lie algebra. We have this. Okay, radical G is solvable. Then by Lee's theorem, we have common eigenvector, right? There exists V from V such that x times V is lambda of x times V for any x from radical G. But we want to say that the space of such vectors is entire V. What we want to prove, that all space is given by this scalar. Here, okay, one can but x times let's denote the common eigenspace by V lambda. Then we know, then I claim that x V lambda belongs to V lambda for any x from G. From this it follows, so it's sub-representation, right? It follows that V lambda from V sub-representation, then, but we know that it is non-trivial sub-representation. We know that it is irreducible. It follows that V is equal to V lambda from this. Therefore, it's not trivial, but by Lee's theorem we have something in V lambda. It's non-trivial that V is equal to V lambda. Okay, but how to prove this? Well, you already know the method. You have to compute something. Okay, you want to let V from V lambda, and we want to show that. Okay, again, let here say Y. Sorry, we want to show that Y times V belongs to V lambda again. So we want to check what is x y v. Okay, again it is y x v plus x y v. This is lambda of x y v, and this is what we can say about commutator of x and y. This is this belongs to radical, right? So this is plus lambda of x y v. Right. And as we, now I want to say that as we did in Lee's theorem, you can do like this. The same computation will show you that lambda of xy is 0. It's entirely the same. By the same computation as in the proof of Lee theorem. Okay. So therefore we will see that this is indeed invariant. So we are done. And now, okay, let me give a definition motivated by this. Right. And what about this? It's it's obvious again because it's commutator, then it is 0, as we did here. It belongs to radical and it's commutator. Then it has upper triangular matrix. Then it is 0. Okay. So now this motivates the following definition. But we don't want, so the algebras where we have this are bad. What are good algebras? When we do not have any elements here, right? But what does it mean? It means that radical commutes with a, if this guy is 0, it means that radical is in fact center. Okay, it could be some subset of center, but it's the maximum of all body other than it's center. So definition. The algebra G is called reductive. It's called reductive if radical of G is equal to center of G. And for these algebras, okay, at least we do not have elements which we cannot distinguish by fine dimensional representations. Okay, and I think let's take a break. And okay, let's take a break for 10 minutes and continue at 5:53. define something. We already defined reductive algebra. That's not bad. But now the problem is, we have 5 classes of algebras: nilpotent, solvable, reductive, semi-simple, and simple. As we know, semi-simple, simple algebras are semi-simple as well. That's good. And now, how to check that something is reductive or semi-simple? Yeah, I forgot to say. Let me mention once again why we are interested in this solvable, reductive, semi-simple algebras. So I already said that there is a radical and the quotient is semi-simple, but it's a natural question: can we lift quotient to the algebra itself? Because quotient is not Lie subalgebra of G, right? But can we lift it? And the answer is yes. There is Levy. Okay, this Levy theorem. That for any G, there exists GSS inside G, such that GSS is isomorphic to G over radical G, and G is equal to sum of its semi-simple and part and radical. And this sum is as vector spaces. I hope that we will prove this theorem, but later. So we can, in principle, we can do it. It's rather technical. And here, this theorem really follows from the fact that second cohomology group of Lie algebra with coefficients in any finite-dimensional module is 0. We will prove it later, I hope. And the proof is parallel to the proof that any representation of Lie algebra is completely reducible. This fact follows from the statement that Lie algebra cohomology, first Lie algebra cohomology with coefficients in any finite-dimensional representation is 0. And this is a theorem about second cohomology group. Okay. But this really reduce, in some sense, the study of arbitrary algebra to semi-simple and just a simple part and solvable part. Okay. And now, from Levy's theorem, it follows that reductive Lie algebra is, yeah. No, it's not direct sum of algebras. It's direct sum of vector spaces, as vector space. Yeah, for reductive Lie algebra, it follows that, in fact, yeah, from Levy's theorem. Okay, sorry. So it's first, and the second, okay, let's say is Levy-Maltsev theorem. The second part, one can ask, can we find really? Okay, the second part is said that all these liftings are conjugated by means of the corresponding group, in fact. So in other words, they are all the same. So moreover, all lifts, all GSS are conjugated. But in order to strictly formulate it, I need to define group or something. Okay, let's. And this is what proved. This is Levy's theorem. This is Maltsev's theorem. It was proved by Maltsev in 1942, something like this. This is in 1905. Okay. Now from Levy's theorem, it follows that reductive, if G is reductive, then G is just direct sum of semi-simple part and its center. Okay, we're GSS to G over center. Moreover, here it's direct sum of Lie algebras because okay, center is convolution with anything, so it's direct sum of Lie algebras. Okay. I mean, I do not say this, but in fact yes, but it's modulo something, so I cannot say that I can give you proof immediately, right? But in principle, yes. Moreover, reductive Lie algebras is just Lie algebras for which representations are completely reducible. But this is not also completely true because representation of abelian Lie algebra is not necessary. So it's necessary to say something here. But okay, now it's like this. But as you see, so in order to prove that some algebra is reductive, now we have how to check that some algebra is reductive or semi-simple or something like this. I hope now we understand that okay, that semi-simple algebras are good, like good part of theory. Solvable is bad part of theory. So we want to study good part of theory. But how to prove that something is semi-simple or reductive? And again, there is common practice is to use some bilinear forms. So invariant bilinear forms. Bilinear forms on a Lie algebra. Let's consider some to motivate definition of this. So we have you already have definition in your sheet, but okay, to motivate it, let V be some vector space, and G be a group. Okay, let's say Lie group. What does it mean that we have invariant bilinear form on vector space V under the action of G? Okay, suppose that G acts on V. What is invariant bilinear form? What is invariant bilinear form with respect to action of G? Okay, we have form. I think it is like this, just right. Just action of group preserve bilinear form, right? This is invariant bilinear form, obvious definition. Now, if it is Lie group, what is invariant bilinear form under the action of Lie algebra? So it's common. So in this course we don't know groups, but probably you know something. So if you are group, you have Lie algebra. If you have representation of group, then it descends to representation of corresponding Lie algebra. And what is invariant form with respect to Lie algebra action? What we can say about this form? If we differentiate it, suppose that we have some way in the group such that G of 0 is identity and G of t, G of 0 dot is equal to some x. What then you have? So you have this equality, right? Can you differentiate it? And consider at t is equal to 0. What we will have? Here is not 0, but here is not. But here you will have what? So we will have x vw, right, plus xw. Okay? And this, so let's just differentiate. This is invariant bilinear form under the action of Lie algebra. Okay? So just differentiate this. But now suppose that our action is a joint action. Then what we'll have? If our representation is a joint representation, then how can we rewrite this for a joint representation? Because this is bilinear form on some vector space V, but we want bilinear form on the algebra itself. So, okay, how we can do it? We know a joint action on the algebra. Let's apply this. What we will have? X, Y, Z plus what? X plus Y X Z is equal to 0. Okay? And this is definition. We call definition bilinear form on G is called invariant if this is true for any X, Y, Z. So I can just give definition from the beginning, but I want to show you that it follows really from group action. So it's natural definition, because if we define it from the beginning, it looks like something arbitrary. But now it's not arbitrary. Okay, and it turns out that there is how we can associate with Lie algebra some invariant bilinear forms. Let V be any representation. You already see that structure theory, like structure theory itself, it looks like something about Lie algebras itself. But now we see that I always say something about representations. You see that to study a structure theory, you have to use representations. That's common phenomenon. So if V is any representation, then one can define the following. Okay, let's say rho V. Then I want to define the following form. It's trace over V of rho of X, rho of Y. Let's define bilinear form by means of this formula. Okay, it is obviously bilinear form because trace is bilinear on each argument, right? Is it obvious this is bilinear form? Okay, bilinear because it's linear. If you multiply by number, trace. Okay. This is moreover it's symmetric bilinear form. This is symmetric bilinear form, okay? And it is invariant. And is invariant. Is it obvious that it is invariant? But let's check what is written here. Here it's written something like this: X, Y, Z minus. So if we apply a representation, it's X, Y, Z minus Y, X, Z. And here you have trace. And here you have trace. Okay. Here you have trace of yeah, I mean, I forgot to say that, okay, we get this, but in definition we have something different. So it's written like this: X, Y, Z is equal to X, Y, Z. How to deduce this from this? is it written correctly? Let's check. So once again, x, if it is this x, y, z, then x, y, z plus, I think I have to use Jacobi identity as well here to get this. So first of all, here I use that it is symmetric in some point, but I think it is the same. No, I do not use it as symmetric. I just have to shift z and x. Here we'll have minus sign. Yeah. So let's x, y, z plus is equal to y, z, x. Okay, it's the same. But now, okay, is it x, y, z, and z, x? So it looks like a little bit different. X and y, shift x and y. Okay, and this is the same. Okay, yeah. So therefore, I want to probably use this. Yeah. So here you have trace x, y, z minus z, and here you have trace of what? Of x, y, z again minus x, z, y. But okay, trace of sum is sum of traces. This and this are the same, and this is cyclically permuted, right? X, just x, x, z, y. If you perform cyclic permutation on the set on some product, then the trace is the same. Property of trace. Like xy, yx, and xyz is equal to zxy as well. Okay, therefore it's symmetric bilinear invariant form. Symmetric invariant form. And you can associate it with any representation. But if you have Lie algebra, you have one special representation, always. But okay, probably you can say, okay, you have always trivial representation. That's true. It's also some special because it's not really always you have trivial representation, as I said in the previous lecture. Trivial, I mean that it acts on zero-dimensional space by zero. Okay, sorry, one-dimensional representation. Trivial one-dimensional representation. Everything acts by zero. But it's not always like it's something, some feature of your algebra that you have one. Matrix algebra do not have any one-dimensional representations. Okay, so a special feature to have one-dimensional representation. But it's not what I want to say. Okay, for trivial representation it will be zero identically. It's not really very interesting. But you have a joint representation, right? And we could give definition. This trace form for a joint representation is called Killing form. Definition. Killing form. Killing form on G. It's K of xy is equal to trace of add x, add y. Like you have some special form, but you can assign this form for any representation, but for a joint representation it has proper name. And now, as it is written in your exercise sheet, we have the following theorem, which we will prove next time. First, Lie algebra G is reductive if and only if there exists representation there exists representation such that B is non-degenerate. Second statement is that, again, everywhere here characteristic should be zero. It's characteristic zero statements. Lie algebra G is semi-simple if and only if killing form is non-degenerate. And third, so Lie algebra G is solvable if and only if killing form on G and GG is equal to 0. So you see that it is pretty strong tool to prove that something is reductive, solvable, semi-simple. So you have to just compute some simple thing and you get this. Okay, any questions? So we'll start the next lecture from the proof. We will prove this theorem. And okay, so now let's move to the problems. But let's not start from the problem let's start from problem number 1. No. Let's prove that the algebra GL2 is reductive. Can you prove that the algebra GL2 is reductive using this theorem? Consider the algebra GL2K over a field of characteristic 0. Can we prove that GL2K is, okay, let's say GL2C is reductive. So one way is to compute its radical, right? To show that it's equal to its center. It's not really, it's possible, in fact it is true that GL2C is equal to direct sum of SL2C plus C times E, where E is just 1, 1, 0, 0. And then you can prove that this algebra is simple, and then it turns. But it's some analysis, you have to compute some commutators and so on. But can we prove that this algebra is reductive using this? So it's enough to find some representation where the corresponding trace form is non-degenerate. Then it's automatically reductive. But GL2C have some special representations again. Do you know some representations of GL2C? It's killing form, but probably if you know the theorem, it's bad idea because it is not semi-simple. Then killing form is degenerate. So, but we have another representation. Which one? Tautological. GL2C acts on C2. Okay, who can compute this form for C2? So B, okay, let V is equal to C2, BV of XY is equal to what? To trace of just XY, just trace of product. Now the question, is this form degenerate or non-degenerate on the 2x2 matrices? Let's recall some linear algebra from the first course. Why? How to see is simpler. So this is symmetric bilinear form. What do you know about symmetric bilinear forms? They correspond to what? In one-to-one correspondence with quadratic forms, right? So it's so we can compute quadratic form, trace x squared, the corresponding quadratic form. It's enough to show that this is the one degenerate, then the corresponding bilinear form is also known. But now it's not hard task. Can you compute this quadratic form? Just could you multiply two matrices? Compute it. Just compute. I mean, we can work with this as well, but this is simpler. Like with quadratic forms, it's always simpler to work. Okay, let me say that we have x1 1, x1 2, x2 1, x2 2. You have to compute square of this matrix. Okay, maybe do you want to compute it and show that it's not degenerate? Could you? You want to write something during lecture, so now you have a chance. No, yes, because it's trace. Okay. Like probably in the first course you have question why we study quadratic forms and bilinear forms, but it's not useful at all. But here we use it. But okay, it's not completely true. You have analysis with this Sylvester criterion. Okay, now, is this form degenerate or non-degenerate? How to check it quickly? Do you know some statement about quadratic forms? Each quadratic form can be represented by, like, how it called, principal axis, главным осям. Do you know, like, it's called Lagrange method to put quadratic form into principal axis? Or alternatively, you can write matrix of it and show that it is not degenerate. But probably if we don't want to compute a lot, we can perform change. Okay, suppose you have form xy on two-dimensional space. Is it degenerate or not? xy on R2, on C2. Okay, what is the matrix of quadratic form? You forgot something. You forgot stuff about quadratic forms. We want to prove that this is not degenerate. It's also without. Okay, so okay, let's. You could say what you want to say. Or okay, in fact, we want to prove it for any field of characteristic 0. Oh yeah, oh no, for R as well. Okay, for sure we want to prove it for R as well. How and how you can prove it? But if you change base, so it's unfortunately probably it's not invariant. You cannot compute GNF by orthogonal change of bases. You know, so you have some change of base, and then this function is not invariant under conjugation. Quadratic form is not invariant under conjugation. It's only invariant under like CX C transpose. So you cannot use GNF. But okay, what I want to say is that you could say, okay, x12 is like x minus y, and x21 is x plus y. Do this change of variables. Then you get that this is in new variables, it is x11 squared plus x22 squared plus 2x squared minus 2y squared. And it is obvious non-degenerate, because it has matrix like this, 1, 1, 2, minus 2. Okay? Okay, thank you. So this is non-degenerate, then our algebra is reductive automatically. Very good. But can we, okay. Now, if I ask you to prove that SL2C is semi-simple algebra, how can you proceed? In fact, we have two options here. Can you say me which two options we have? So next task is to prove that SL2C is semi-simple. Oh, we have three options, in fact. Yeah, if we know that GL2C is direct sum, if we compute center of it, and we will show that center is this, then this is semi-simple. So in fact, it's enough to prove this decomposition and plus that center of GL2C is equal to C times identity. But I hope this is more or less obvious. Okay, you can compute how to prove the center only scalar matrices. Yeah, that's all more or less the same problem. Yeah, but it's just some computation you apply to matrices with identities 0, 1, 0, 0, and something. Okay, and why this is true? So the center is this, but now we want to prove. Okay, it's still not completely enough because center is this. And okay, the quotient is something. Why the quotient? It's enough to prove that not really this. It's enough to prove the quotient of GL2C over this is SL2C. But how to prove it? Probably I can use some homomorphism theorem, or you can just prove that it's direct sum. Then, but it's like it's more than we want. But from the other side, we know that it should be a sum. But why, do you know why GL2C over C times E is isomorphic SL2C? Probably, can you use some homomorphism theorem here? First homomorphism theorem. We want some map from GL2C, for example, to GL2C, such that the kernel is center. I know such map, but probably, yeah. So it's a joint map, but yeah, the kernel center, but image is not clear what is image. But probably clear. Okay, any suggestions? How to prove this or this? Okay, maybe this directly. You mean that you want to apply GL2C to GL2C, right? And x to x minus trace of x times identity, right? Okay, kernel here. Why? So if we have scalar, okay, yeah, I see. So then scalar matrices in this. Is it homomorphism of Lie algebras? It's obvious, in fact. Why? Because this is in the center, and it computes with everything. So we want to show the commutator of xy is equal to commutator of this guy with this guy. But it is true, because this commutes. So this is homomorphism. What is the image? Image of, so we know that the image belongs to matrices with trace 0, right? But otherwise, but from the other side, we know that that the kernel is one-dimensional, so the image should be three-dimensional. And traceless matrices, 2 by 2 matrices, also have dimension 3. Then it's equal to image is SL2C. Okay, but probably it's instructive to do it directly, because for SL2C we have special basis, which is called, in mathematics it's called E, F, and H. In physics it's called like X plus, X minus, and X0, I suppose. It's like Pauli matrices, in fact. Okay, and then it is basis of traceless matrices, but it's obvious, like now, that this is direct sum, just by construction. Okay. So this is first, this is first possible way to prove that SL2C is semi-simple. What is second way? Yeah. Yeah, because image first of all, image is traceless matrix. Kernel is one-dimensional. Then image is isomorphic to quotient of GL2C over kernel. It is three-dimensional. Then the image is three-dimensional. But we know that dimension of traceless matrices is 3. Then it should be the same, like three-dimensional vector space. Image is isomorphic to three-dimensional vector space. It is some three-dimensional vector subspace of traceless matrices. Мы имеем образ, это подпространство, трехмерное подпространство в матрицах со следом 0. Ну, а матрица со следом 0 это трехмерное пространство. Значит, подпространство, трехмерное подпространство в трехмерном пространстве это само пространство. But probably it's easier than this, you know. Okay, what is second possibility to prove that your algebra is semi-simple? Okay, Killing form. Let's compute. So it's like task 1A. Let's compute Killing form for SL2. Can somebody do it on the blackboard? Could you? To do it, you have to let's write commutation relations for SL2 because you compute adjoint action, you need it in this basis. What is commutator of E and F? No. H, okay, it's commutator, let's write it, E and F is H. What is commutator of H and E? I just want to write it in some particular order because it's common, therefore. What is commutator of H and E? Who knows representation theory of SL2C? So what is commutator of H and E? But you could compute, but from representation theory. But it is three-dimensional representation of SL2C. What is highest weight for three-dimensional representation? But okay, let's just compute. Okay. We will discuss representation theory of SL2C anyway because it's part of structure. It's not 0 as well. No. Plus 2e. 2e. It's like, you know, the film is like Джентльмены удачи. It's like, girl, yes. Minus 2f, yeah, right. Okay, now you can compute Killing form with this information. Just write matrix of Killing form. Okay, anyone is familiar with bilinear forms and what is matrix of bilinear form? Is it okay? Okay. Yeah, only 3. Okay, let's compute Killing form. So what is matrix of form? We just choose basis and write matrix like K of EI, EJ in the. Let's choose an order of basis as follows: EHF. EHF, yeah. EHF. Then matrix will be better. But what is Killing form? It's trace of what? But write the formula. K of xy is equal to what? Напишите формулу k от xy равно trace x. Okay, so you have to. So add x is some 3 by 3 matrix, right? But why you write for E0? Is it obvious 0? Why? I think that something could be not 0. It seems that we need to write explicitly 3 matrices: add E, add H, and add F. Right? Let's write explicitly these matrices. It should be 3 by 3 matrix. But let's use order EHF as well. I mean EHF order. What is how to write matrix of linear operator? You should in first row, in first column, you should put 0, obviously, yes. In second, what you want? -2, 0, 0. Okay, -2, right. Yes, okay, good. Let's write add H. It's easier. Good. And add F. Okay, and now we have to compute traces of products of these 6 products and 6 traces. Okay, it's nilpotent matrix. 0, yeah. H naught. H is equal to 8, right? And for f is 0. And it is symmetric, so we have to only compute 3 numbers, right? So now we want to multiply E and H. But it's obvious 0 again. But E and F probably non-zero. E and F non-zero, I think. Yeah, it's obviously non-zero. But you have to compute 3 products of some things. You have 2 on diagonal, 2 on diagonal, and 0 on diagonal, so it's 4. Four, not 0. Because it's minus sign and minus sign. And obviously, for H and F, it's obviously 0 because you multiply like strictly lower triangular matrices by diagonal. So 0. Okay, so here again 4, 0, 0. Okay. Okay, and now, and what we see is that this form is non-degenerate, obviously, right? Then SL2C is semi-simple. Thank you. And what is the third way to prove that SL2C is semi-simple? But it's like we already, in some sense, did it. Yeah, we can just prove that it is simple. Then it is semi-simple as well. And how to prove that it is simple? We have to show that there are no ideals at all. But, okay, it's some computation. Let's try. I start with arbitrary element A1E plus A2H plus A3F. And I want to show that consider commutators with elements, I can obtain any element. But we see that, suppose that obtain element, let's say H, let's say AH. Suppose that H belongs to ideal. Then E belongs to ideal as well, and then F belongs to ideal as well. Then we are done, that our ideal is SL2C itself. And the same is for, I think the same is for any element. If we have E and ideal, we have H and ideal, then we have F. So if it's enough to show that we can just get one element. Okay? But here probably you have some cases where A1 is non-zero, A2 is non-zero. Suppose that A1 is non-zero. Then what we can do? So our purpose is to get E. Let's first of all we can consider commutator with H, right? Then we will kill this guy. We will get what? A1 EH is minus 2A1 E plus commutator of FH. FH is minus 2F, is plus 2F plus 2A3 F. And now what? Okay, probably if okay, it's not really important that we want to get E, we want to get any basis element is now. Now I consider commutator with F. Okay, then it is equal to something non-zero times H. So we get H in our ideal, so we are done. But okay, but you see that it's the same with other cases. You could check it. So it's easy to prove that SL2C is simple, really. Then it is semi-simple as well. Okay, so what else we have in our... Okay, 1b. Prove that the Killing form for an nilpotent algebra is 0. Is 0 that it's like identically 0, just 0 form? Killing form is this. Okay, let's think. But why add x is nilpotent? Why add x is nilpotent? It's not an, it's easy part. Like if x is nilpotent, then add x is nilpotent. Add x is nilpotent, that just follows from definition of nilpotent algebra. Because if you apply add x a lot of times, then you get 0. It's just definition. It's not Engel theorem, it's just definition. But you can say in Russian. No, but okay, but no, it's not called nilpotent, and it's called ad nilpotent. Because otherwise it's easier to, because in fact any abstract algebra is concrete algebra, it's bad to see. So we say that it's ad nilpotent. Any element of nilpotent algebra is ad nilpotent. So therefore Killing form is identically 0. Is what is written is converse true? Is it true that if is it true that we have Killing form identically 0, then your algebra is nilpotent? How it helps? But probably at least probably we need for this question probably we need to use 3. Okay, from 3 it follows that it is solvable. But we have some additional. It's not only it's some solvable algebra which. So if we have counterexample, it should be only solvable. So therefore it should be some subalgebra of upper triangular matrices. The question is, can for solvable algebra Killing form? Suppose we have solvable non-nilpotent algebra. Can Killing form be identically 0? Why? but like we should, but we don't work with matrix itself. We work with add x. So we have x. It has non-zero number on diagonal. That's true. But we want to compute add x first. Is it possible that add x? So is it possible that add x is always like? Yeah. Yeah. If all add x nilpotent, then we know by angle theorem we know that our algebra is nilpotent, right? So suppose that it is not nilpotent, then there exists some add x which is not nilpotent. Yes. Yes. And what? So like all degrees of add x are non-nilpotent. But what? But suppose that k of add x is equal to 0. And what? But why? It's just add x squared. Like trace of add x squared is equal to 0. It could be some matrix such that which is not nilpotent. But probably we want to some series. What you say that we should use all degrees, but here we have only one. For all degrees it can, but how we can use? Yeah, for all degrees it cannot, but it's like how we can use it. Да, ничего. Okay, let's discuss. You could think about it. Let's discuss next time. But because we have 20 minutes, let's do something which we need for homework. I want to say. Okay, problem number 2 is about. So it is counterexample to the following statement. So let's read the first statement of theorem carefully. It said that Lie algebra is reductive if and only if there exists some representation such that the associated with the representation form is non-degenerate. But one can ask, okay, suppose that we have arbitrary bilinear form, so it's not necessary that any symmetric bilinear form associated with some representation. You know, so like we have some invariant bilinear forms associated with representation, and we have all bilinear forms, symmetric invariant bilinear forms. And one can ask, is it true that probably if we have some invariant symmetric bilinear form, then your algebra is not necessarily reductive? But it is not true. So this is a counterexample where we have some Lie algebra where you have some non-degenerate invariant bilinear symmetric form, but it is not reductive. So this is therefore here it's important that it's really representation. Okay, but let's skip it. It's like just some counterexample. It's not really very important. Just counterexample to this statement. Let's do problem number 3. It's like update of this computation. let's show that GLN is a reductive Lie algebra. Like multiplication of two matrices revisited. Yeah, so tautological. We have tautological representation of GLN, and let's compute the corresponding form. Or probably it's simpler to do it with trace x squared, right? What is it? We need some, suppose that our matrix is x11, x1n, xn1, xnn. Okay, can someone say me what we have here? Or probably, so it's simpler first of all to write here, right? It's just product of matrices and then apply x, like xyj is equal to xgy. Okay. Probably now it's simpler to write this because it's just some formula. Okay, and how it looks like? What is diagonal element of the product of two matrices? So it's sum of what? Of x, I, some k, let's say, but y, k, I. Right? And just sum of these guys. Sum over k over xik, yki over ik from 1 to n, right? Correct? Now if we apply what? Yka is equal to x, yk, what we will get? You will have x11 squared plus xnn squared, right? Plus 2, right? Or I less than j, xij, xji, right? The question is this form is okay. Sorry, this is squared. Okay, and is this form non-degenerate or not? Why? Okay, you can just play the same game, for example, or you can prove some inequality. You know, so there's some. So this is. I know inequality you cannot prove, but yeah, but just do for each pair xij xgi do this, and you get some form with some signature. For C you do not have any signature. For R you have some signature. It's an interesting question. Like for non-degeneracy, give you a reductive or non-reductive, but what signature gives you in the case of real Lie algebra? And there is so the answer is given in the problem number 5. For example, it said that if your Lie algebra is Lie algebra of some compact Lie group, then Killing form is negative semi-defined. And in fact, the reverse direction is also true. So if you have Lie algebra such that Killing form is negative semi-defined, then it is Lie algebra of compact Lie group. So therefore отрицательно полуопределена, то есть она отрицательная, но может быть либо отрицательная, либо ноль. Ну, то есть ядро может быть. Правда. No, not so. It's true if it is like if it is negative defined, then it is like also simple, so it will be compact simple Lie group. And compact Lie algebra will be simple, or semi-simple, and fact simple. That's not true. That's problem number 4. It says that for simple Lie algebra, you have only unique invariant bilinear form, but only for algebraically closed field. But otherwise, it's not true. You have a lot of form because you have form for each representation. But in principle, like it's not what we want to get. Like from the beginning, we have a lot of forms. So it's surprising that for simple algebra only one, because simple algebra still have a lot of representations, but they are all proportional. Okay, so then GLN is reductive. Okay, deduce from it that SLNC is semi-simple. We know, like again, the center of GLN is just scalar matrices. Then GLN is direct sum of SLN and scalar matrices. Then okay, SLN is semi-simple. But you see that, okay, but now we can try to, it was three ways to prove that SL2C is semi-simple. But as you see, let's try to prove that SLNC, it's easier to prove it using this, because you use obvious form, which is easy to compute. But now, if you want to prove that SLNC is semi-simple using Killing form, then it's pretty bad, because now matrices will be n squared minus 1 times n squared minus 1 matrices, where they're really big. But anyway, it is possible to do it like this. Okay, without using that on simple algebra, you have only one form. How? I mean, we can try, but when we compute, it was 3 by 3 matrices. But for GLN, see, it will be n squared minus 1 times n squared minus 1 matrices. They will be really big. So in principle, it's possible, but it's pretty hard. We can't. Мы можем посчитать форму Киллинга для SLN, но ее тяжело считать, потому что это будут такие матрицы n в квадрате минус 1 на n в квадрате минус 1, очень большие. И еще какие-то не очень понятно, там, какие они, там, базис желательно убрать. То есть, в принципе, можно, но как-то выглядит не очень. But can we reduce the complexity of this problem of computing Killing form for SLNC by some insights? Yes, and we did it. It's simple. But now we have problem. It shows that SLNC is simple by computing its Killing form. But do you have any hypothesis how Killing form looks like? But keeping in mind that, okay, probably like it's really hard without any knowledge, but in these exercises we have a lot of knowledge. For example, probably you feel that SLN is, I already said that SLN is simple Lie algebra. Therefore, by problem 4, it should be only one form, at least for algebraically closed field. But some invariant bilinear form, it corresponds to tautological representation. It's just trace of product. Therefore, like by this, we know that Killing form also should be trace of product. But now we can say, okay, we don't know anything, but we want to prove that Killing form is trace of product. Like we see answer in DeepSeek or ChatGPT, and now we want to prove it. How to prove it? Like now we want to prove that it is scalar, and we want to compute scalar as well. scalar times times trace of xy. Like, we do not need to use it. We just, it's like our hypothesis. We know that it should be like this. If we know that it should be like this, then we can prove it. And we will not use problem number 4 for it. We let's just prove that it is trace times something. But how to prove it? I said it at the beginning. We still don't know. Yeah, it's not. We didn't prove it. It's possible to prove it more or less directly. Just compute some commutators. It's pretty simple, pretty semi-simple. Okay, so. But now I just want to say that let's try to. Can we? But okay, we have only 5 minutes. Okay, maybe in 5 minutes we will not do it, but you should think how to prove easily without, reduce computations. We know answer, we want just to prove that the answer is like this. How to do it? We have to compute something, but very small amount. Okay, but now maybe let's do 5a, because it's a little bit different, and it is what you will have in your homework. Let's prove that UN. Do you know what is UN? It's the algebra of unitary group. UN is some complex matrices, and it's the algebra of Rieuli group. As you know, it's complex matrices, then it should be complexly group. That's wrong. It's not complexly group. You know that UN is compact, right? But any compact complexly group is abelian. Okay, X from matrix that X is equal to minus X transpose conjugated, right? So this is the algebra, and we want to show that it is reductive. And moreover, we want to show, there is another, show that UN is semi-simple. Okay, let's show that it's semi-simple. Let's show first that it is reductive, okay? And then we can compute center and see that it is. That's not true. This is wrong. Sorry. It is not semi-simple. It should be reductive. Sorry. It's misprint. It's reductive. It's not semi-simple because it has center. Semi-simple is SUN with trace 0. Again, we can play the same game. And what is difference? What is difference? How to prove that UN is reductive? You have to, it's real algebra, okay? It's real algebra. So the form will be real valued. Okay, how it looks like for n is equal to? What you have here, 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 and here. What you have on the diagonal? No. Yeah, purely imaginary number. Here you have bi. And here, if I will have c plus di here, then here you have right? So it should be minus transpose conjugated, but minus. If you consider minus conjugated, it will be minus c plus di. Okay? And what we can say about form, how it looks like in this case, it is minus a square. I just consider this formula and substitute there's this minus a squared minus b squared and plus 2 times I mean, okay, I already compute quadratic form, but okay, this is the same. Plus 2 c plus di times minus c plus di. What is it? It's minus absolute value of this complex number, right? It's minus 2 c squared plus d squared. Absolute value squared, sorry. Okay, this is indeed real values as it should be. Moreover, it's negative definite. It's negative definite. Yeah, it's negative defined. It's negative. So therefore, it's not degenerate by definition. So it's reductive. To show that Killing form is negative defined, as you know, it's like more or less the same as 3v. We should compute Killing form, and the insight is that Killing form is again trace of product. So it's really Killing form up to some multiplier, but okay, unfortunately, yeah, we do not have time. But probably we'll do it next time. Something for here, because anyway we will spend major part of next lecture on proving this. I mean, probably entire lectures, because this is very important. This is called Cartan's criteria. This is called Cartan. So next lecture we will just prove this theorem. C. Cartan is from C. Ну, по-русски ска. По-английски C. Okay, so homework, you have homework. After next lecture, I will release exercise sheet, which is necessary to solve. It will consist some harder problems. Maybe I already said that, so what I can include there. And not a lot, some. It will be a pretty small list, but of some problems which are more interesting than. Посложнее, да, но это как бы семинарский, тут просто как подсчеты какие-то. То есть on the seminars we will compute something, because it's a lot of computations in this list theory, concrete. But on the exercise sheets we will have something like more theoretical. Okay, so that's it.